Hi guys, today we're going to be looking at our notes for electrochemical cells, or last time we were referring to these as voltaic or galvanic cells, and these are just terms to describe a really simple battery. So last time in class we looked at like a zoomed in picture of the different half cells, and we talked about what reaction was taking place at each cell, where you guys had reduction and oxidation happening, and we kind of put it together. What you're going to be doing today is just kind of filling out some of the notes with me in regards to what we talked about last time in class. And then we will be taking a look at some problems where you guys are going to be doing standard cell notation to describe the chemical reaction that's occurring. So let us begin. Why is this not working? Okay, so we have an electrochemical cell, right? So this is just our half cell setup where you guys have the apparatus to make some electricity, which is a flow of electrons occurring from a thermodynamically favorable redox reaction. So it's a reaction that likes to happen. You don't need to force it to happen. If you just connect everything with the wire, electrons will start to flow. So we have two different half cells. And you guys remember within the half cell, one cell is responsible for doing oxidation. And then you have another cell that's responsible for doing reduction. And then when you put it together, you guys have this flow of electrons that has been created. Number two, we have this little bridge, the salt bridge that exists between the two half cells that's connecting the two half cells. Last time I did it in class for you guys, it was just this filter paper that was soaked in something that was an ionic solution. I used potassium nitrate, but it could be any ionic solution that you would really like. And the ionic solution itself just needs the positive and negative ions. Oh, but a disclaimer is you don't want to actually use an ion that is involved in the chemical process, because that'll mess with your cell potential, but just any other ions that are positive or negative. And they just allow for this transfer of electrons to occur between the two different solutions that you're looking at. This is a picture of what our half cell setup looked like from last time. So we had an aqueous solution of zinc sulfate. We had our zinc electrode. On the other end here, we have our solution of copper chloride, and we had our copper electrode here. So this is solid zinc that we're looking at. This is solid copper that we're looking at. And these are the ions that we have. So copper 2+ and zinc ions. And we saw this reaction take place over here. In our left cell over here, we had a reaction occur where there was a loss of electrons that was happening. So we had our solid zinc losing electrons to turn into zinc 2+ plus 2 electrons that were now free to go up in this wire. Anytime this loss of electron happens, we're looking at an oxidation reaction. And you guys remember an ox red cat, right? So an ox is just a little helpful mnemonic to help you remember that for oxidation, we have our anode, right? And this is just the name of our half cell. And then for the copper side, this one has to be reduction, because again, we're not going to get a flow of electrons if you just have oxidation occurring. So we have a cathode over here. Right. And reduction is how everything is written actually in our CERP table. You see this loss of electrons that's occurring. So I'm sorry, a gain of electrons that's occurring. We have our copper 2+ gaining 2 electrons from the wire. And it is going to solidify and turn into solid copper and then add on to the mass of the copper electrodes. And remember, this is just a review of last time, but the mass is going up here for the electrode. The mass is decreasing inside the zinc electrode. Another thing I kind of briefly talked to you guys about when you guys were doing the potato lab last time, but this anode where a loss of electrons is occurring, you have a buildup of electrons over here. So we would call this a negative electrode. So the anode is always negative. And over on the other end where you guys have a less on this side, there's a less buildup of electrons. The electrons are traveling over to this side. We would call this the positive end of our battery. So when you guys look at your little Duracell batteries and you guys remember there's a positive end and a negative end, it's really describing like what chemical reaction is actually happening on that end of the battery. You have a reduction happening over at your positive end, and we have oxidation occurring on our negative end. So that's why you guys see the sign over here, negative and positive. When we do electrolysis, we're going to see that the signs actually end up changing, and we'll talk about that next time. And we have like this travel of anions and cations that are coming to the specific sides. But for a regular typical battery, we're looking at anode negative, cathode positive. Okay, and then the next slide, we're just going to go over and fill all this out. So we have electron flow, right, occurring through our wire. We're going from the negative end to the more positive half cell, right? So we're flowing from zinc to copper. The copper ions are the ones that are picking up electrons, and therefore they're getting reduced, right? And we could also write something called the cell diagram instead of drawing out these half cells and doing all that. It is nice to see it visually, but this is just a shorthand way to describe what is happening. We always put the anode on the left side and the cathode on the right side. We talked about this last time in class. And remember, at the anode, right, we have oxidation occurring here, the loss of electrons, zinc turning into zinc 2+. And at the cathode, we have reduction happening here. We have the gain of electrons. So copper 2+ plus 2 electrons will turn into copper solid. So this is just describing what we just talked about. We have zinc 2+ ions that are being made inside our anode, our zinc half cell. And then over on the other end, we have copper 2+ turning into copper, right? And take note as well, as you guys are turning solid zinc over into zinc 2+, as our oxidation is occurring, we're getting a lot of positive charges building up in our solution. So remember that little like salt bridge that is connecting our two different half cells here, right? That filter paper. To balance out the buildup of all these extra positive charges that we have, negative charges are going to flow out into this solution. And then on the other side, where copper 2+ is turning into copper, we end up getting a buildup of negative charges, right? So like the positive charges are disappearing, and now we have all these negative charges left over from the solution of copper chloride, right? So the chloride ions are left behind. And to really balance out that negative charge, we're going to have a flow of positive ions coming out of the salt bridge to balance out this buildup of charge. When we draw this cell diagram, or not draw, sorry, when we write out the cell diagram, this is just a reminder that we always go anode to cathode. So I always remember this air conditioning AC. So you have A on the left and your cathode is on the right. But when we draw out, like when you physically draw out, here's my half cell and here's my wire and here's my salt bridge, and you connect everything with your electrodes, it doesn't necessarily have to be anode on the left and cathode on the right. Sometimes you'll see a cathode here and then the anode here, right? So how can you tell which one is which? Well, you need to look up what is happening using the CERP tables, and then from there you can kind of figure it out. And we'll look at some examples of that today. Okay, so this single vertical line that we have right here, right, in between zinc turning into zinc 2+, is just telling you that we have a phase change occurring from solid to aqueous. The double vertical line we have in our cell diagram, right, it represents a salt bridge, or it's just a division between the two half cells that we have. Sometimes you guys might have an electrode that actually doesn't react, like it's something that is inert, right? This, you would need an inert conductor, like an electrode that gets put into whatever is changing over here, because you need a metal to obviously pass the electrons through. But if the substance itself is not going to be aqueous, like for example, that standard hydrogen reaction where we're producing gas, right? you guys might see something like this where you have platinum here, which is our substance that is making up our inert conductor electrode, but it's not actually going through a reaction, but we're just putting in parentheses like, oh, platinum is actually there. It's what's conducting the electricity. But like this is the thing that is actually happening. You have hydrogen gas turning into H+ ions, or your H+ ions turning into hydrogen gas, right? And this is just a reminder that the platinum electrode is there just to help the electron transfer from one cell to the next. Okay, so we're going to go through and use our SERP table that you guys have in your notes, and we're going to write out cell diagrams for the following combinations of electrodes we have. So what we saw earlier, if you could pause the video over here. Actually, I'll do one sample with you guys. Then I'd like you to pause the video, and then I'll give you guys the answers for the remainder 3 that we have. So one of the first things you want to do is you want to go into your table and look up these reactions. So I'm looking up the reduction reaction happening to zinc, right? And I just find this on my table. And our potential for that is minus 0.76. For fluorine, on my table, this is the reaction that is occurring between fluorine gas turning into 2 fluoride ions, and the potential for that is 2.87, right? So these are both reduction reactions, but we know that one of them is going to be oxidation, right? You can't have 2 reduction reactions happening, then you don't have a flow of electrons, right? So you are going to figure out the most positive number that you guys see over here, the 2.87, the largest value for the cell potential. This is the reaction that's actually going to happen. So fluorine gas will get reduced and turn into these 2 fluoride ions. So I know like this is a go, right? So this is our reduction reaction that's occurring. And reduction, remember, is occurring in our cathode, right? For this one over here, I know that this chemical reaction is less likely to occur. I have a negative value over here, and I know that this actually is going to get flipped or reversed, right? So we have zinc solid losing electrons and turning into zinc 2+. And when I flip this reaction, I know that this value is going to become positive 0.76 is what you guys are looking at here. This is my oxidation reaction, right? And anox, this is the anode, right? So from here, it's really simple after you guys have determined what reaction is actually occurring to come up with your cell diagram. Right, so remember our notation is going to be A to C, right? So we have the anode and the cathode. So at the anode, we have oxidation occurring. I'm going to make a little line. I have my zinc solid turning into zinc 2+, aqueous. And on my cathode side, I have reduction occurring over here. I have fluorine gas changing into 2 fluoride ions that are, let's see. Oh, I didn't put the symbol for this one. You don't have phases. If they don't have phases, don't worry about it. But I'm just going to write aqueous for this right here. Yeah, so this is going to become your cell diagram for this. And I know that I don't have to change any of the coefficients because we're dealing with 2 electrons that are lost and 2 electrons that are gained. All right, so go ahead and pause the video and do the other 3. And then when you guys come back, I'll have the answers for the 3 problems up. All right, you guys, so that was a lot of writing, but you could go through and see that we did the same procedure. So I went through and I looked up the equations first for each of these reactions. And then I drew a box around the one that was more positive. So like this one, the 0 is more positive than negative 0.4. So I know this is getting reduced. This one is, again, a bigger number than negative 0.044. So I knew this was getting reduced. And then for the iron turning into iron +2, this was more positive. So I knew that that was getting reduced. The other reaction, you want to flip and turn it into an oxidation reaction. So all you have to do is flip the products and the reactants, and then the cell potential will change in terms of its sign. It goes from negative to positive every time you flip it. So that's kind of what's going on over here. And this last one is a good one to note. The oxidation one doesn't have the cell potential changing at all. Remember, this is our standard state, so that's still 0, but we flip everything. Another thing to note too is the coefficient changes. I need 2 electrons lost and I need 2 electrons gained, right? So which is why you have, I introduced a 2 in front of this iron reaction that was occurring over here to make sure that we have 2 electrons that are getting transferred. One thing that I will talk to you guys about next time, Thursday when I see you guys in class, is notice here, typically if you were to do multiply a reaction by a coefficient, you would multiply that value by that same number, right? But it doesn't get multiplied. And we'll look at this together. I wanted to give you guys a better explanation for what voltage actually is. And we'll talk about that in class on Thursday. And this is just one of those ones where if you flip it, the sign changes, but if you multiply it by a coefficient, the numerical value for that voltage doesn't change. And we'll talk about why next time. So what you see in purple, this would be your cell diagram notation. And if you have any questions on this, make sure you ask me about it next time we have class. And then the last and final part, you guys, for today's video is we are going to be looking at how do we calculate the cell voltage for the entire battery. So we're looking at everything put together. You have the 2 different half cells, you have your reduction and your oxidation occurring. And I want to know what is your cell potential, or what is your voltage like for this battery setup that we actually have. And we call this electromotive force, right? Keep this term in the back of your mind as we talk about what voltage actually is on Thursday as well. So this is sometimes called EMF, or a lot of times you'll see it as just your E, right? With your cell potential, a little 0 here to indicate we're dealing with standard state. And then the cell is telling you it's like the overall of like 2 cells that we're actually looking at. I will tell you guys that the method that you guys see over here tells you do the right-hand side of your cell notation minus your left-hand side. Or another way to say this is you take your E of the reduced minus the cell potential of the oxidation reaction, and there's a negative sign right here. So when you flip the oxidation one, you're going to change the sign, and then the negative comes right here. But I actually like this method a lot more, because we kind of already do it when we're writing out your cell notation. You guys remember back on the prior slide over here, every time we flipped the oxidation equation and we wrote it like from here original, right, over to like here, the brand new equation of what's actually happening for oxidation, I took my cell potential and I made it positive like this, right? If you do that, you've already done the work of figuring out what the actual potential is for that chemical reaction. And all you have to do is then just add up the values of the 2 half cells. So we just add them up together. So going back to here, like if you guys were to find the E of the cell of this battery system that you guys have, you would take 0.14, that number, add it on to our reduction number, which is 0. So it would be 0.14. Right? The one that you guys see up here, we'll do the zinc and the fluorine one. The cell potential for our battery here, it would just be our oxidation cell potential, the 0.76. And remember, we flipped it, so we made it reverse. And then you just add it to your reduction one, right? And the total of that would become your voltage for this battery cell that you created. Okay, so this last problem, if you could pause it and then go ahead and try this out, and then you guys will see the answer when you return. All right, you guys, so for the first one, I went through and I used some hints that were given to us in the problem. We have a silver electrode, and then here we have a hydrogen electrode. We know the total cell voltage is 0.80. And then you're also told that hydrogen is the more negative electrode. So we know that this is the one that has to get flipped, and it'll be the one that is getting oxidized. So this is anode over here at the hydrogen one. So I knew I had to flip my hydrogen reaction. So I flipped it from the standard cell potential way of writing it on the SERP table. The sign of this, you don't have to worry about. It's just 0, right? So it's going to stay 0. And then I knew for the silver reaction that it was going to stay the way that it was because you have reduction occurring over here. And then our cell potential for that is 0. Or 0.80 for this half cell reaction that is going on. One note here is you might be wondering where the 2s came from inside our silver one, and it's because our hydrogen reaction has 2 electrons reacting as hydrogen turns into hydrogen ions, and then silver only had 1 electron reacting. So I had to multiply it by 2, meaning I gave it coefficients over here. When I am trying to calculate what the total is over here, right? We know that our total of our battery setup has to come out to 0.80, right? The hydrogen one is our standard. I know that one has to be a 0. So I know that this number here has to be 0.80, and that's how I got that value for the silver reaction that is occurring over here. And because it's reduction, I don't need to add a negative sign to it. Like this is my actual answer for what the standard potential of the silver electrode is. And you could also check, right? You could check your SERP table and you see, oh, it is 0.80. The second problem here, we have now silver being combined with an aluminum electrode. And one more time, you're told which one is more negative. So we know that that's getting oxidized. We know the total voltage for our battery. So like the 2.46, this is the total. It's our E cell. And then what you're trying to do is after you write out your cell diagram, we want to figure out what is the standard electrode potential of the aluminum. So you could go like, well, can't I just look it up in my table? And the answer would be, yeah, right? You could actually go and just check it out. But if this is a problem where you're only given limited information and you're given like one of the reactions that you know, then you could kind of use that. And if you didn't have a table, then this is telling you how would you figure it out. So this is kind of a more like realistic AP problem because you guys don't get the table. You'll only have access to limited information that's told to you guys. So for here, we know the silver electrode potential because we calculated it from here. So this is where the 0.80 is coming from. I know that aluminum also is more negative, right? So this is where we are going to have oxidation happening, which means that this has to be our cathode that we have, right? So let me go ahead and box this because it could be. And actually, I messed that up. So I was looking right above, which is confusing. Okay, so aluminum is the more negative electrode. We have oxidation happening, right? So we know that this is going to be taking place. The aluminum reaction will be our anode, right? We have aluminum turning into aluminum +3 over here. And I wrote out the chemical reaction for that right there. The cathode, that means that silver has to be reduction occurring. Right? Oops, did I mess this up? Okay, no, this is good. So anode oxidation, right? We have the more negative reaction occurring over here because we're going to have to flip it, right? The cathode, we have our reduction happening. So this is just a silver reacting in terms of how you would normally expect it to react with reduction. So our normal SERP table values that you guys are seeing over here. So our job now, after you have your cell diagram written out, and quick note, my diagram isn't completely correct because notice here for aluminum, we are dealing with 3 electrons moving. For silver, we only have 1, right? So we know that this is going to tell us that we need to take our reaction and multiply it by 3. So I'm going to add coefficients of 3 to this. And again, next time in class, I'll talk about why this number doesn't change though. So even though you multiply the reaction by 3, your voltage isn't changing to 2.40. And we'll talk about why. So we have these values. We know that the total has to come out to 2.46. So I know that 2.46 has to come from our potential value for the anode reacting. So I'm going to call this X, right? And our cell potential for the cathode, which we know to be our standard reduction reaction occurring, and it is just 0.80 that we acquired from above. The anode, though, be careful, because we know that at our anode, we actually have oxidation occurring and not reduction. So whatever number you actually calculate to get the standard reduction potential, it's going to be the reverse of that. So that's why this is a negative sign right here. All right, so you go through, you would calculate this out. For the X value, I got negative X is equal to 1.66. So I know that my value here for our aluminum reaction, when it goes through reduction, not oxidation, is going to be negative 1.66. Remember, we flipped it to get it to be oxidized, right? Which is why if you're doing the E for this part right here for the oxidation reaction, it's 1.66 positive. So 1.66 plus 0.80 is going to give you guys that positive 2.46 number. One of the most common mistakes that people will make with a problem like this is just the sign, right? Forgetting that, oh, at the anode, we actually had to flip the reduction potential. So you're going to deal with this being the number that you guys would actually see on the SERP table. And that is all. I will see you guys next time.